Folks, last week when I posted my video to get us going in topic two, I can't remember if I was on problem 6.5 or 6.19, and I mentioned this idea of exponential smoothing. And once a value of alpha has been chosen, that gives us one snapshot of what a possible forecast would be given the value of alpha, and then of course the complement 1 minus alpha as they are applied to the time series value and the forecast respectively. If you recall, in the problem in 6.5, we had an alpha value of 0.20, which left a forecast multiplier of 1 minus 0.20, which is 0.80. And I think I made the point that while that is one forecast for one chosen value of alpha, it would be very simple in Excel to go through a whole list of possible combinations of alpha and 1 minus alpha to come up with the best forecast for the data that you have. And I think I just said that, and that's not a nice thing to say without actually performing that for you in Excel. So I thought I would follow up and show you how we do this. So what I'm going to do is I'm going to go back to this set of data that we have for 6.5 part C. And remember, we had looks like we had 6 data points, and there's the time series value or the actual value. And the time series value alpha, the multiplier, we started with 0.20, so the forecast would have been 0.80. What I'm going to do is I'm going to go through in increments of 1/100th. I'm going to go through the possible combinations of alpha and 1 minus alpha, and I'm going to compute the mean square error for each combination of alpha and 1 minus alpha. So what I did in my spreadsheet, if you go back and look at the video, I think I had 20% here and 80% here. So I went in and I changed these, and the alpha value I have linked to this column of potential alpha values again in increments of 1/100th all the way down to 1 at the bottom. And then here I just have a formula to compute the complement of whatever value is here. So this cell is equal to 1 minus whatever I have in F19. And I have applied these alpha values in 1 minus alpha respectively to the time series value in the forecast. And I have come up with forecast values for, let's see, weeks 2 through 6, and then I have computed the mean square error of each week. What I have done, so once I go through that for the combination of 0.01 and 0.99, I get a mean square error of 18.48. And over here, I have just said I have taken the average of the values in cells, let's see, E17 through E22. That's fine because that's going to be 0 since the forecast value is always the same as the time series value to kick off an exponential smoothing drill. So this is how, and again, so what I want to do very quickly, if I wanted to do this by hand, I would have to go back and change these. I would have to change this to 2%, and then copy whatever the mean square error is over into this column. And that would take quite a bit of time. But there is an easy way to do this in Excel. And this is what I wanted to show you. If you go to Data, and we'll use this technique at length in week 8 when we get into simulation. Probably good to show you this now. So again, go to Data, go over here to Forecast, and click on the What If analysis, and click on Data Table. So what this is going to do is it's going to help me replicate the mean square error for all combinations of alpha. And of course, once I know the alpha value, I know the 1 minus alpha, which is picking up the portion of the forecast as opposed to the portion of the time series value or the actual value. So what I want to do is I want to replicate mean square error for all the values in these columns. So the column, let me actually do this first. Let me highlight the table that I want to populate. So this is the table that I want to populate. And let me go back to What If Data Table. And what I want to do is I want to change this mean square error for the column inputs in the alpha column. So I'm going to put a column input cell of this top value here. It looks like N6. And hopefully when I punch OK, this table will populate with the mean square error that is related to the chosen value of alpha. And you can see, and again, remember, how would I have to do that if I wanted to produce this table? If I didn't have this option, I'd be doing it by hand and going back and changing the value of alpha, so on and so forth, and then copying over the mean square error. So this has populated for me. And again, what it's doing, for example, in this case right here, it substituted 0.06 as the alpha value, and then it would be taking the complement of that, or 0.94 or 94%, and using that as the multiplier on the forecast to come up with a mean square error of about 16.3. I think the next thing that's of interest here, and you can do this very quick, and obviously the question is, which of these is the best estimator for alpha? And so what I'm going to do this visually just so we can see what these look like. So if you highlight both the alpha and the mean square error, and you go up to, let's see, insert, and here in the middle we got some charts. And if we put this in a scatter plot, here what you can see, and I'll make this a little bit bigger so it's very clear what's going on. What you're getting here is you're getting on the horizontal axis, you are getting values of alpha from 0 to 1 in increments of 100. And then on the vertical axis, you're getting the measurement of the mean square error. And of course, remember, what we're looking for here is for that error metric to be as small as possible to show that the forecast is aligning fairly well with the time series value or the time series data. So you see, we start a little higher up here, and then we continue to decrease the error metric until it looks like the bottom is right around, I would say, somewhere between 0.3 and maybe about 0.42. And we can validate that here in just a minute. So about 0.35 to 0.42, that is really the sweet spot for the error metric for this data. I'm sorry, I should say for the value of alpha for this data. And then obviously you can see that the error metric continues to climb from there. So about let's say about 0.35 to 0.42. Let's see, 0.35 to 0.42. Let's see. Yeah, it looks like 0.0692. It actually looks like the value of alpha that produces the smallest error metric is about 0.37. Now, typically, when we would go through this as an analyst, we'd probably pick these in increments of a tenth, not 100. But again, you can see the value of digging through this a little bit and trying to be a little more precise. And the beauty of it, folks, is really just a couple of clicks in Excel, and you can really kind of hone in on these smoothing constants to help you out. So just kind of a midweek thought that came to me that I should show you this. And again, I hope this is helpful. And any questions, let me know. There's obviously, depending on the data that you have in your time series or in your time series itself, the plot that I just showed you, let me just pull that back up one more time. This curve that you see here is not always going to be the case. It will be dependent upon the time series value, and then of course the increment of alpha that you choose. This thing can go all over the place. What I would really challenge you to do is, if you've got a couple extra minutes, number one, it would be good for you to be able to set up and use that data table, because again, as I said, we'll use it exclusively in Chapter 8 when we get into simulation. But just create some crazy data and go through this and plot the value of alpha and the error metric and see how this changes and try to convince yourself why it changes. And that would be a good discussion to have this week. If anybody wants to take one of these and try to go through that and then post it on the class discussion board, we could certainly go through that. So again, I hope this is helpful. Take care and have a great week.